Above the poles of our planet, an unseen yet powerful force is at work. For decades, scientists theorized its existence long before we had the tools to measure it. This global force plays a crucial role in shaping Earth's atmosphere and even dictates the path of charged particles escaping into space. It might also explain why some planets lose their habitability. This mysterious force is known as the ambipolar electric field, and it may be just as fundamental to our planet as gravity or magnetism. Fortunately for us, it's not too strong because if it were, Earth might look a lot more like Venus. Thanks to groundbreaking observations from NASA's Endurance mission, scientists have now directly measured the ambipolar field for the first time. This milestone solved a puzzle that has lingered since the 1960s. It also confirmed what researchers have long suspected: Earth is governed by a third global energy field complementing the magnetic and gravitational fields we already know. I'm Alex McColgan, and
you're watching Galactic Will.
Today, we're diving deep into the invisible, electrifying mystery of Earth's ambipolar electric field. This is the story of how a subtle force powers the polar wind, influences our atmosphere, and helps determine our planet's ability to support life. We're already familiar with Earth's other major fields. The magnetic field, often visualized as loops surrounding our planet, acts as a protective barrier. It shields us from the sun's high-energy particles and dangerous cosmic rays. Without it, our atmosphere would be much more vulnerable. Then there's Earth's gravitational field, the ever-present pull that keeps everything grounded and helps retain our atmosphere. It also plays a vital role in understanding sea level rise, climate change, and ocean currents. Now, with a new paper published in Nature on August 28, 2024, we have confirmation of a third global energy system. Let's explore what this newly measured ambipolar field really is and why it matters. To begin, we must talk about plasma. Plasma is a state of matter like solids, liquids, and gases, but it's far more energetic. It's made up of ionized particles where electrons have separated from their atoms. Plasma makes up about 99% of all visible matter in the universe and is responsible for phenomena like auroras and lightning. On Earth, plasma forms in the upper atmosphere, about 90 kilometers above the surface, where gases are thin enough to allow ionization. These ionized particles, mostly lightweight and fast-moving, get trapped along magnetic field lines. While most of this plasma is confined by a boundary called the plasma pause, spacecraft in the 1960s noticed something unusual: a supersonic wind of charged particles flowing from Earth's poles into space. These included cold hydrogen and oxygen ions, which shouldn't have had enough energy to escape. This discovery challenged the prevailing belief that Earth's magnetic field lines were closed loops. The notion of a one-way escape route dubbed the polar wind began to emerge. But what was driving it? Solar heating alone couldn't explain how cold particles were moving so fast. Scientists suspected an additional force was at play. In 1968, researchers proposed that this was caused by an electric field spanning the upper atmosphere. However, it was believed to be too weak to measure with existing technology less than half a volt. Efforts to find it stalled for decades. Then, in 2016, a clue arrived from our planetary neighbor. The Venus Express mission from the European Space Agency detected a 10-volt electric potential around Venus, over 5 times what scientists expected. This raised an important question: if Venus once had water, could its strong electric field have stripped it away? This prompted researchers to ask whether Earth, too, had an electric field, and if so, why had it not lost its water like Venus? Estimates suggested Earth's electric field might be as weak as 0.3 volts, but even this could have a profound effect on atmospheric escape. Enter NASA's Endurance mission. Designed specifically to measure this feeble field, the mission required a breakthrough instrument, the photoelectron spectrometer. This tool was engineered to detect the faint slowdown of electrons escaping Earth's atmosphere, an effect of the planet's electric field. The Svalbard rocket range in Norway, the northernmost launch site on Earth, was chosen as the perfect launch point. On May 11, 2022, a suborbital rocket carrying the spectrometer was launched into the magnetic North Pole, reaching an altitude of 768 kilometers. It gathered data for 518 kilometers before splashing down just 19 minutes later in the Greenland Sea. During this brief but crucial flight, the instrument detected a change in electric potential of 0.55 volts between altitudes of 250 kilometers and 768 kilometers. This direct measurement confirmed the existence of the ambipolar electric field. As small as 0.55 volts may seem, it's exactly the right amount to drive the polar wind and explains how cold particles can escape without being heated. This discovery opens a new chapter in our understanding of Earth's atmosphere. So, what exactly is happening in this region of space? The ionosphere is the key. It starts around 80 kilometers above sea level and stretches out into the exosphere, which reaches 10,000 kilometers from Earth. It overlaps with the magnetosphere and is teeming with ionized gases. Here's how the ambipolar field forms. High-energy photons from the Sun collide with light elements like hydrogen and oxygen in the upper atmosphere. This knocks electrons free in a process called ionization, leaving behind positively charged ions. The lighter electrons naturally rise, while the heavier ions are tugged back by gravity. But because electrons and ions are electrically attracted to each other, this movement creates a vertical electric field. That field is the ambipolar electric field. This field acts like a gentle but persistent tug-of-war. The electron's upward motion slightly overcomes gravity's pull on the ions, allowing some of them to escape into space. This is the engine behind the polar wind. And unlike thermal escape mechanisms, the ambipolar field doesn't need to heat particles to fling them into space. This explains the cold plasma escaping Earth's atmosphere, something that puzzled scientists for decades. It also explains why Earth's upper atmosphere is puffed up higher than expected. The field causes heavier ions like oxygen to behave as though they're half as heavy, which expands the scale height of the ionosphere by 271%. We're not just losing particles into space, we're losing specific types. Earth sheds about 3 kilograms of hydrogen gas every second, totaling 95,000 tons per year. It also loses 1,600 tons of helium annually and smaller amounts of heavier gases. These losses occur through a mix of mechanisms, including thermal escape, charge exchange, and of course, the polar wind. Still, there's no need to panic. These losses are tiny compared to the size of Earth's atmosphere. We won't run out of oxygen for at least 1 billion years, and even then, it would take another billion to lose our hydrogen-rich oceans. But over geological time, these small losses shape the evolution of planets. This is why Venus's stronger electric field matters. With a 10-volt potential, Venus's atmosphere would have been far more vulnerable to particle loss, especially water's components hydrogen and oxygen. Over time, this could help explain how Venus transformed from a water-rich world into a dry, inhospitable planet. In contrast, Earth's relatively weak ambipolar field may have protected it. It allowed for just enough particle escape to balance atmospheric processes without stripping away life-sustaining gases. And now, having finally measured it, scientists can explore its full role. Could it help us better model space weather, understand climate change, refine predictions about habitability on exoplanets? NASA is already preparing a follow-up mission named Resolute after another historic Arctic ship. It will take more detailed measurements and help us answer these deeper questions. We're still at the beginning of this discovery, but what we've learned so far is enough to change how we understand our planet and others. The ambipolar field isn't just an invisible quirk of physics. It's a vital part of why we're here. And doesn't that feel electric? Above Earth's poles, a subtle yet profound force operates, a force that, until recently, remained undetected. This force, known as the ambipolar electric field, plays a crucial role in shaping our planet's atmosphere and influencing its habitability. Hypothesized over 6 decades ago, it has now been directly measured, marking a significant milestone in our understanding of Earth's atmospheric dynamics: the discovery of the ambipolar electric field. In May 2022, NASA's Endurance mission embarked on a groundbreaking endeavor to measure this elusive field. Launched from the Svalbard rocket range in Norway, the suborbital rocket ascended to an altitude of approximately 768 kilometers, traversing the polar regions where the ambipolar field's effects are most pronounced. During its 19-minute flight, Endurance collected data revealing a change in electric potential of 0.55 volts between altitudes of 250 and 768 kilometers. Though seemingly minuscule comparable to the voltage of a watch battery, this measurement confirmed the existence of a global electric field influencing atmospheric particles. Understanding the ambipolar electric field. The ambipolar electric field arises from the interaction between electrons and ions in the ionosphere, a region extending from about 80 to 600 kilometers above Earth's surface. Solar radiation ionizes atmospheric gases, creating a plasma composed of free electrons and positively charged ions. Due to their lower mass, electrons tend to escape Earth's gravitational pull more readily than heavier ions. However, the electrostatic attraction between these charged particles generates an electric field that binds them together, facilitating a collective movement known as the polar wind. This bidirectional field, termed ambipolar from the Latin ambi meaning both, exerts an upward force on ions, effectively lifting them to higher altitudes. For instance, hydrogen ions experience an upward acceleration 10.6 times greater than the force of gravity, enabling them to escape into space at supersonic speeds. Implications for Earth's atmosphere. The ambipolar electric field significantly influences the structure and dynamics of Earth's ionosphere. By lifting ions to greater heights, it increases the ionosphere scale height, the altitude over which atmospheric pressure decreases by a factor of approximately 2.718. Specifically, the field boosts the scale height by 271%, allowing the atmosphere to remain denser at higher altitudes than it would otherwise. This process contributes to the continuous loss of atmospheric particles into space. Earth loses about 3 kilograms of hydrogen and 50 grams of helium every second, amounting to approximately 95,000 tons of hydrogen and 1,600 tons of helium annually. While these losses are not immediately concerning over geological time scales, they play a role in the gradual evolution of Earth's atmosphere. Comparative planetology, Earth and Venus. The study of the ambipolar electric field extends beyond Earth, offering insights into the atmospheric histories of other planets. For example, the European Space Agency's Venus Express mission detected an electric potential of about 10 volts around Venus, significantly stronger than Earth's 0.55 volt field. This potent field may have contributed to the loss of water from Venus's atmosphere by accelerating the escape of hydrogen and oxygen ions, the constituents of water molecules. In contrast, Earth's weaker ambipolar field has allowed it to retain much of its water, highlighting the field's role in planetary habitability. Understanding these dynamics is crucial for assessing the potential for life on exoplanets and the long-term stability of their atmospheres. Future research and exploration. The confirmation of Earth's ambipolar electric field opens new avenues for research into atmospheric physics and planetary science. NASA plans to conduct follow-up missions, such as the upcoming Resolute mission, to further investigate the field's properties and its influence on atmospheric escape processes. These studies aim to deepen our understanding of how electric fields shape planetary atmospheres and contribute to their evolution over time. The detection of the ambipolar electric field marks a significant advancement in our comprehension of Earth's atmospheric dynamics. This subtle yet pervasive force plays a vital role in regulating the escape of atmospheric particles, influencing the structure of the ionosphere, and potentially determining a planet's capacity to support life. As we continue to explore the intricacies of our planet and others, the ambipolar electric field stands as a testament to the complex and interconnected forces that shape planetary environments.